Welcome back. In front of us, we have a question that reads, a mass of 0.18 kilograms of water at 100 degrees Celsius is mixed with 0.72 kilograms of water at 36 degrees Celsius. Calculate the final temperature of the water given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Solution: if we should analyze this problem, we have water that is at 100 degrees Celsius that is mixed with water that is at 36 degrees Celsius. So the general idea that you have to understand is whenever you have two substances and one of them is having a higher temperature than the other, when these two substances mix, there will be a temperature that will be attained by both substances, and that is called the equilibrium temperature. So in short, the water that is at 100 degrees Celsius will eventually lose heat in order to increase the temperature of water that is at 36 degrees Celsius. So meaning that the temperature of water that is at 36 degrees Celsius is going to increase to attain a stable equilibrium temperature. Okay, so we call that temperature theta 2. Always remember, the hot object will always lose heat. The object with the lower temperature will always gain heat. So this is how heat is transferred until equilibrium is attained. So we want to know the final temperature that is going to be attained by the water. We can call this water as A and the water that is here as B. The heat loss by water A will be equal to the heat gain by water B. This is always an important law in thermodynamics. The heat loss by one substance must be equal to the heat gain by the other substance. So what is the quantity of heat loss by water A? We can call that QA. This will be equal to the quantity of heat gain by water B will be QB. So since there is a change in temperature for both cases, this will be mass of body A, the specific heat capacity of body A, multiplied by delta theta, that will be equal to mass of body B, the specific heat capacity of body B, multiplied by change in temperature. So remember, we are using Q is equal to MC delta theta. If we should emphasize on the change in temperature, let's say mass of water A, specific capacity of water A, into, since the body is losing heat, that is from 100 degrees Celsius, the highest temperature will be 100 minus its final temperature, let's call it theta 2. So this is equal to, for water B, we're going to say the mass of water B, the specific heat capacity of water B, times the change in temperature will be from the final temperature minus the initial temperature. That is theta 2 minus the initial temperature is 36. Remember, for a body that is losing heat, the change in temperature will be the initial temperature minus the final temperature. But for a body that is going to gain heat, the change in temperature will be the final temperature minus the initial temperature. So we know that for water B is going to attain a higher temperature than its initial temperature, okay? But for water A is going to have a lower final temperature than its initial temperature because it is the one that is losing heat. We know that we are dealing with the same type of substance, that is water. So because we are dealing with water, it means that the specific heat capacity is the same. So we can say Ca is equal to Cb. That is the specific heat capacity for water A is the same as the specific heat capacity of water B. So we can make this equation simple for ourselves by cancelling the specific heat capacities. So that is, we're going to have mass of A into 100 minus theta 2 is equal to mass of B into theta 2 minus 36. So what is the mass of water A? That is 0.18 kilograms. Okay, it is the one that is having a temperature of 100 degrees Celsius. The mass of water B is having 0.72 kilograms. So that is the one with the temperature 36 degrees Celsius. 0.72 kilograms. So we can say mass of A is 0.18 into 100 minus theta 2. This is equal to the mass of B is 0.72 into theta 2 minus 36. 0.18 times 100 is 18 minus 0.18 times theta 2 is 0.18 theta 2. This is equal to 0.72 times theta 2 is 0.72 theta 2 minus 0.72 times 36, that is 25.92. So what can we do? We can collect like terms. Minus 0.18 theta 2 minus 0.72 theta 2. This is equal to minus 25.92 minus 18. So minus 0.18 minus 0.72, that is minus 0.9 theta 2. So this is equal to minus 25.92 minus 18 is minus 43.92. Negative signs will cancel out. So we're going to have 0.9 theta 2 is equal to 43.92. To find theta 2, we divide both sides by 0.9. 0.9 cancels 0.9. Theta 2 will be equal to 43.92 divided by 0.9, and that is 48.8 degrees Celsius. So that is the final temperature that is going to be attained. It is also called the equilibrium temperature. All right, 48.8. To summarize, the water that is initially at 100 degrees Celsius will attain a final temperature of 48.8. Okay, it is the water that is having the higher temperature, so it is going to lose heat. The water that is initially at 36 degrees Celsius will have its temperature raised to a final temperature of 48.8 degrees. Okay, so this is the general idea here. Ice of mass 0.21 kilograms at minus 10 degrees Celsius is mixed with 0.43 kilograms of water at 77 degrees Celsius. Calculate the final temperature of the water. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Specific heat capacity of ice is 2,100 joules per kilogram per Kelvin. Specific latent heat of fusion of water is 334,000 joules per kilogram. Solution: we have ice that is initially at minus 10 degrees Celsius, and we have water that is initially at 77 degrees Celsius. These two substances were mixed. So what is going to happen? The substance that is having a higher temperature is going to transfer heat to the substance with the lower temperature. So that is always how heat is transferred. So meaning that this 77 degrees Celsius water is going to lose heat and thereby is going to have a decrease in temperature to have a lower temperature than its initial temperature. So this ice that is at minus 10 degrees Celsius is going to increase its temperature to become water at a steady temperature. So we can call that temperature that is attained, that equilibrium temperature, as theta 2. Okay, so meaning that the water is going to decrease its temperature to attain theta 2, while ice is going to increase its temperature to attain the steady temperature theta 2. But how will be the transformation for ice? Because it is a solid initially, it has to become water. So if we draw our heating curve, we have temperature in degrees Celsius, and let's say we have ice at minus 10 degrees Celsius at this point here. That is ice. So if it is at minus 10 degrees Celsius, its temperature can rise, okay, to 0 degrees Celsius of ice. So this is ice at 0 degrees Celsius. So from ice at 0 degrees Celsius, what is going to happen? It is going to become water at 0 degrees Celsius. That is here. And from water at 0 degrees Celsius, we can now increase its temperature to the equilibrium temperature theta 2. That is here. So which means for the ice itself, it has to go through 3 stages of transformation. This is stage 1, this is stage 2, and this is stage 3. That is, if we have the water that is at 77 degrees Celsius mixed with the ice that is at minus 10 degrees Celsius initially, the ice at minus 10 degrees Celsius first have to become ice at 0 degrees Celsius. Then from ice at 0 degrees Celsius, it has to become water at 0 degrees Celsius. From water at 0 degrees Celsius, it will attain the equilibrium temperature. So the ice is going to gain heat while going through those 3 stages of transformation. So what can be the equation that we can develop for all the 3 stages? First, for stage 1, we're going to use mass of the ice, the specific heat capacity of the ice, times change in temperature. This formula is for the stage 1 because there is a change in temperature. So for stage 2, let's say plus, when we are considering the stage 2, that is a change of phase. So that will be the mass of the ice times the specific latent heat of fusion. So at stage 3, ice has converted to water and there will be a change in temperature to attain theta 2. So what will be the formula for that? So that will be plus, we can say mass of the ice. If you want, you can say mass of the water, but it's the ice that has converted to water, so we can still use the same mass. Okay, it's the same mass. So it will be the mass of the ice, the specific heat capacity of water, times the change in temperature delta theta. So this is the heat gain by the ice. All right, so if we have to develop this formula again, that will be the mass of the ice, specific heat capacity of the ice, the change in temperature will be 0 minus minus 10, right? For a body that is gaining heat, the change in temperature will be the final temperature minus the initial temperature, so that is 0 minus minus 10 plus the mass of the ice times the specific latent heat of fusion of the ice plus the mass of the ice, specific heat capacity of water, times the change in temperature will be theta 2 minus 0 for the third stage. So that is theta 2 minus 0. If we should simplify this, we'll have mass of the ice, specific capacity of the ice times 10 plus the mass of the ice times specific latent heat of fusion plus mass of the ice times the specific capacity of water. Theta 2 minus 0 is just times theta 2. If we should substitute the values that we have here, what is the mass of the ice? The mass of the ice is 0.21 kilograms times the specific capacity of the ice is given in the question as 2100 joules per kilogram per Kelvin. So that is 2100 times 10 plus the mass of the ice is 0.21 times the specific latent heat of fusion of ice is 334,000. 334,000 plus the mass of the ice is 0.21 times the specific capacity of water is 4,200 times theta 2. Okay, so 0.21 times 2,100 times 10 is 4,410 plus 0.21 times 334,000 is 70,140 plus 0.21 times 4,200 times theta 2 is 882 theta 2. Okay, so that is the heat gain by the ice. So what about the heat loss by the water? The heat loss by water, the water is initially at a temperature of 77 degrees Celsius, so it is going to become water at a lower temperature, which is theta 2. So since there's a change in temperature, we're going to use MC delta theta. Okay, that will be the mass of the water, the specific heat capacity of water times the change in temperature. That will be the mass of water, specific heat capacity of water. The change in temperature will be first the higher temperature minus the lower temperature. Okay, the higher temperature is 77 minus the lower temperature is theta 2. So remember, whenever an object is losing heat, the change in temperature will be the initial temperature minus the final temperature. So going by this formula, what is the mass of the water given in the question? It is 0.43 kilograms of water. So 0.43 kilograms times the specific capacity of water is 4,200 into 77 minus theta 2. So 0.43 times 4,200 is 1,806 into 77 minus theta 2. 1,806 times 77 is 139,062 minus 1,806 times theta 2 is 1,806 theta 2. So what can we do? We can equate the two equations that we have. Okay, these two equations that we have, we can equate them. So by saying heat loss is equal to heat gain, or heat gain is equal to heat loss. The heat loss by the water is equal to the heat gain by the ice. So what is the heat loss by the water? Is 139062 minus 1806 theta 2. This is equal to the heat gain by the ice is 4410 plus 7140, 4410 plus 7140 plus 882 theta 2, 882 theta 2. So what can we do here? We can say 139062 minus 1806 theta 2. This is equal to, we can add 4410 with 70,140. That will be 74,550 plus 882 theta 2. We can collect like terms. We can say 139062 minus 74,550 is equal to 882 theta 2 plus 1806 theta 2. By collecting like terms, if minus 1806 theta 2 is going to the other side, it becomes positive. So 139062 minus 74,550, that is 64,512. This is equal to 882 plus 1806 is 2688 theta 2. To find theta 2, I will divide both sides by 2688. So this will cancel this. So we can say theta 2 is equal to 64512 divided by 2688. So what value is that? Theta 2 will be 24 degrees Celsius. A spherical copper ball of mass 3,290 grams at 300 degrees Celsius is placed in a copper calorimeter of mass 770 grams containing 2,310 grams of water at 36 degrees Celsius. Neglecting heat loss to the surroundings, calculate the final steady temperature of the mixture. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Specific heat capacity of copper is 385 joules per kilogram per Kelvin. Solution. If we should break down this problem, we have water that is inside a calorimeter. The initial temperature of the water is 36 degrees Celsius. Obviously, that will be the initial temperature of the calorimeter as well. So, what happens later on is that a spherical copper ball of mass 3,290 grams at 300 degrees Celsius is placed into this calorimeter. So we have a copper ball that is placed into this calorimeter. Okay, so this is the copper ball. The initial temperature is 300 degrees Celsius. So we have also learned that the calorimeter is also made up of copper. What you have to understand about the concept that we are to use here is that we have a spherical copper ball that is at 300 degrees Celsius that is put in to a calorimeter containing water. So the initial temperature of the calorimeter and water is 36 degrees Celsius, while the initial temperature of the spherical copper ball is 300 degrees Celsius. What will be the nature of heat transfer here? It is obvious that the object that is having a higher temperature is going to lose heat to supply heat to the other objects or substances. So in short, the spherical copper ball is going to lose heat to the water and the calorimeter. So what is going to happen? The water and the calorimeter will attain a higher temperature than their initial temperatures. So the equilibrium temperature that is attained, we can call that theta 2. So how do we establish the equation here? We will say that the heat loss by the spherical copper ball is equal to the heat gain by the copper calorimeter plus the heat gain by the water that is in the calorimeter. So this is the equation. Since there is a change in temperature, for the heat gain by the calorimeter, we can say it is mass of the calorimeter, specific heat capacity of the calorimeter, times the change in temperature, plus the heat gain by the water will be the mass of the water, specific heat capacity of water, times the change in temperature. What of the spherical copper ball? For the spherical copper ball, it will be the mass of the spherical copper ball. So let's say Cu, the specific capacity of the spherical copper ball times the change in temperature. Okay? So we can say the mass of the spherical copper ball, specific capacity of the spherical copper ball into the change in temperature. Since it is losing heat, it will be the initial temperature minus the final temperature. The initial temperature, let's call it theta 3, okay, minus the final temperature for the spherical copper ball will be the equilibrium temperature attained. So that will be theta 2. This will be equal to the mass of the calorimeter, specific capacity of the calorimeter into the change in temperature will be theta 2 minus theta 1. Okay, so let theta 1 be the initial temperature for the water and the calorimeter, that is 36 degrees Celsius. Then plus the mass of the water, mW, times the specific capacity of water times the change in temperature will also be theta 2 minus theta 1. So as you can see, this is the equation that we have to establish. The heat loss by the spherical copper ball is equal to the heat gain by the copper calorimeter plus the heat gain by the water. The question wants us to find the equilibrium temperature that is attained, that is theta 2. For those substances that are gaining heat, the final temperature theta 2 will be higher than the initial temperature theta 1. So that is why the change in temperature will be theta 2 minus theta 1. But for the substance that is losing heat, the initial temperature is higher than the final temperature. So that is why we're going to have a change in temperature of theta 3 minus theta 2, where theta 3 is the initial temperature of the spherical copper ball. The theta 2 is the final temperature or the equilibrium temperature attained. So if we should go back to take the data from the question, it says a spherical copper ball of mass 3,290 grams. That is, the mass of the copper ball is 3,290 grams. So that is 3.29 kilograms. The spherical copper ball is at a temperature of 300 degrees Celsius, and we call that theta 3. So that is 300 degrees Celsius. That is the initial temperature of the spherical copper ball. The mass of the calorimeter, let's call it MC, is 770 grams. So that is 0.77 kilograms. Okay. The mass of the water is 2,310 grams. So that is 2.31 kilograms. The initial temperature for the water and the calorimeter will be theta 1, and that is 36 degrees Celsius. We are given the specific heat capacity of water as 4,200 joules per kilogram per Kelvin. We are given the specific heat capacity of the calorimeter as 385 joules per kilogram per Kelvin. The specific heat capacity of the copper calorimeter is also the same as the specific heat capacity of the copper ball, since both of them are made up of copper. Okay, so we can say the specific capacity of the copper ball is also going to be 385 joules per kilogram per Kelvin. We want to know the equilibrium temperature, so that is what we're going to find. So now let's try to substitute the values that we have in order to calculate the equilibrium temperature theta 2. The mass of the copper ball is 3.29 kilograms times the specific heat capacity of the spherical copper ball is 385 times the initial temperature theta 3 of the copper ball is 300 minus the final temperature, which is the same as the equilibrium temperature, will be theta 2. This is equal to the mass of the calorimeter is 0.77 kilograms times the specific capacity of the calorimeter is 385 into the final temperature is theta 2 minus the initial temperature is 36 plus the mass of the water is given as 2.31 kilograms times the specific capacity of water is 4,200 multiplied by theta 2 minus the theta 1 is 36. 3.29 times 385 is 1,266.65 into 300 minus theta 2. This is equal to 0.77 times 385, that is 296.45 into theta 2 minus 36 plus 2.31 times 4,200 is 9702 into theta 2 minus 36. So we can expand the bracket. 1,266.65 times 300 gives 379,995 minus 1,266.65 times theta 2 will be 1,266.65 theta 2. This is equal to 296.45 times theta 2 is 296.45 theta 2 minus 296.45 times 36 is 10,672.2. Then plus 9,702 times theta 2 is 9,702 theta 2 minus 9,702 times 36. That is 349,272. So this is what we have. We can simplify further. 379,995 minus 1,266.65 theta 2 is equal to 296.45 theta 2 plus 9702 theta 2 will be 9,998.45 theta 2 minus 10,672.2 minus 349,272 is minus 359,944.2. So to collect like terms, we can say minus 1,266.65 theta 2 minus 9,998.45 theta 2. This is equal to minus 359,944.2 minus 379,995. So minus 1,266.65 minus 9,998.45 is minus 11,265.1 theta 2. This is equal to minus 359,944.2 minus 379,995 is minus 739,939.2. So the negative signs can cancel. Therefore, we'll have 11,265.1 theta 2. This is equal to 739,939.2. To find theta 2, I will divide both sides by 11,265.1. So this will cancel this. Therefore, theta 2 is equal to 739,939.2 divided by 11,265.1. So theta 2 is equal to 65.7 degrees Celsius.